Good evening, and welcome to tonight's very special lecture on thermodynamics. Before we begin, I'd like to gently inform you that this is a nonsense lecture. That means nothing I say should be taken seriously or literally or even semi-literally. This is all designed to be soothing, sleepy, and a little bit silly. Just enough to help your brain float into the warm fog of dreams. If you enjoy this kind of relaxing absurdity, I'd be very grateful if you could like the video and subscribe to the channel if you haven't already done so. Not only does it help support what I'm doing, it lets the algorithms know that nonsense is important. This video was made with the help of AI tools. If you're curious about that, you can find additional details in the video description. Now, let's begin our nonsense journey through the world of thermodynamics. Where heat is moody, molecules are dramatic, and the universe is slowly unraveling, like a cozy ball of yarn with strong opinions. Now, thermodynamics, as we all know, is the study of the thermal dynamics of thermally dynamic things. It is often described as the love language of warm toast and refrigerator whispers. Yes, the very whispers that float around late at night when the butter begins to think philosophical thoughts. You may be wondering, what is a therm? Well, a therm is a unit of measurement invented by very tired scientists who accidentally spilled tea on their equations. A therm is precisely equal to the amount of heat required to make one sleepy kitten yawn on a rainy Tuesday afternoon. Scientists argued for decades over whether Mondays or Thursdays had stronger yawn energy, but Tuesday prevailed. Dynamics, on the other hand, are a lot like drama, but for molecules. When water boils, for instance, it's not because it's hot. It's because it's mad. Furious, in fact. Little water molecules bickering like soap opera stars, spinning and slapping each other with vaporous disdain. That's why kettles whistle. They're gossiping. Now let's talk about the first law of thermodynamics. This law very wisely states that you cannot create or destroy energy, only move it around awkwardly, like when you shift in your seat, and the warmth from your thighs disturbs a perfectly cool pillow. Scientists call this pillow disturbance entropy, but we'll get to that soon, or maybe later, or maybe we already did. The second law of thermodynamics is a little more judgmental. It says that everything must become more disordered over time, including your sock drawer, including your dreams, including, perhaps, this lecture. It's comforting, really. Entropy means you're not messy, you're just following the law. A very sleepy thermodynamic law. And the third law is the one about absolute zero, not to be confused with your self-esteem on a bad day, or the amount of chocolate in the cupboard when you need it most. Absolute zero is the coldest cold, the chill that could make even polar bears put on tiny sweaters and mutter about climate change in hushed woolen voices. We will shortly discuss heat engines, but not the kind in cars. No, I mean the tiny imaginary gnomes inside every toaster who take naps between browning cycles. They wear monocles and argue about croissants. One of them is named Reginald. Take a breath, let it settle, and prepare yourself for more drifting nonsense about energy, ice cubes, and the secret emotional lives of steam particles. Reginald, the leader of the toaster gnomes, once wrote a book titled Crumbs and Consequences, a Thermal Memoir. It's sadly out of print, mostly because no one could find a font small enough to publish it. But it's important to remember that heat always flows from hot to cold. Much like gossip at a family reunion, it begins with someone overheated and ends with everyone feeling awkwardly chilled. Now, let's take a moment to consider entropy. Entropy is not just a measure of disorder, it's also the name of a jazz quartet made up entirely of melting ice cubes. They perform one concert, then cease to exist. Beautiful, tragic, slightly damp. Scientists will tell you that entropy increases in a closed system. But what they don't say is that socks mysteriously vanish as part of this process. Where do they go? Some say the fourth dimension. Others say they're recruited by dust bunnies to fight in the Great Lint Rebellion of 1993. Entropy is also responsible for forgotten passwords, tangled earbuds, and the steady migration of Tupperware lids to parallel universes. Now let's talk about calorimetry. Calorimetry is the science of measuring how much heat it takes to make a marshmallow decide it no longer wants to be solid. It's a delicate field, a discipline requiring soft hands, warmer pockets, and a complete disregard for practicality. In laboratories around the world, scientists observe spoonfuls of soup to understand the gentle dissipation of warmth over time. This is known as the broth curve. Very prestigious, frequently misunderstood. Let's not forget thermal equilibrium, a very peaceful state when two objects reach the same temperature and stop arguing. Imagine a cup of tea and a countertop finally finding common ground. The tea says, I'm cooling off. The counter says, I know. I've been here before. This moment, this perfect moment, is often ruined by a cat. But such is the way of thermodynamics. Let's pause here for a moment of meditative reflection. Let yourself imagine a warm pile of folded towels. Not freshly folded, no. Folded 3 hours ago. Still warm, mysteriously. Science cannot explain it, but you feel safe. The universe is cradling you in a cotton polyester blend. In the next section, we'll explore the 0th law of thermodynamics, the law so important they named it after nothing. But first, perhaps, a sip of chamomile, a yawn, and the slow realization that none of this matters. And that is the beauty of nonsense. The 0th law of thermodynamics is perhaps the most mysterious of them all. It was named after the others, and then retroactively inserted at the beginning. That's like showing up late to a dinner party and being declared the host. Quite bold. Now, the 0th law states that if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is also in thermal equilibrium with object C. In other words, everyone's chill. If everyone's chill. Some interpret this as a cosmic hug. Others believe it's the universe's way of saying, let's all just calm down. Now picture 3 sleepy muffins on a windowsill. One is warm, one is cooler, and one is just right. Over time, they become the same temperature and start a jazz trio. That's the 0th law in action. It's also the origin of what scientists call the muffin constant, which has yet to be accepted by the broader community, but is widely respected among napkin physicists. Let's turn now to the Carnot cycle. Oh yes, the Carnot cycle, named after Nicolas Leonard Sadi Carnot, who once tried to cool soup by sighing dramatically into it. The Carnot engine is considered the most efficient engine possible under ideal imaginary conditions, involving reversible processes, perfect insulation, and an audience of polite molecules who never interrupt. The Carnot cycle consists of 4 stages: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic forgetfulness. That last one is often omitted from textbooks, but it's very important. It's the stage where the engine forgets what it was doing, stares into space, and then quietly continues. Much like you, perhaps, right now. Now, you may be wondering, what does adiabatic mean? Ah, a beautiful word. Adiabatic comes from the ancient Greek phrase adiabatikos, meaning without a hat. In thermodynamics, it refers to a process with no heat exchange. But spiritually, it's the art of maintaining your own inner warmth, even when no one else is sending good vibes. Let's pause again and just imagine a single ice cube placed carefully on a velvet pillow beneath a chandelier, whispering, "I do not melt for anyone." But of course, it melts. That is its destiny. And so, the Carnot engine turns, a quiet dance between heat and work, between expansion and compression, between logic and the irresistible lure of nonsense. In our next section, we'll explore thermal radiation, the emotional volatility of photons, and how microwaves feel about being ignored at dinner parties. For now, let your thoughts drift like helium balloons in a library, aimless, weightless, delightfully lost. Thermal radiation is the process by which objects emit energy in the form of electromagnetic waves. But what most textbooks don't tell you is that these waves are dramatic, passionate, full of feelings. When an object is warm, it begins to radiate, not just heat, but intent. A toaster, for instance, doesn't simply glow. It announces, "Look at me," it says. "I am ready to char." All objects do this. Even you. You too are radiating, though not in the main character at prom way. More like a cozy, lukewarm jelly bean in a sweater kind of way. Now, there exists a theoretical object known as the black body. Despite its mysterious name, it is not a noir detective. It is an idealized physical body that absorbs all incoming radiation and emits it perfectly without a single complaint. Scientists study black bodies because they are dependable. They never lie. They just sit there, absorbing your doubts and radiating your truths. One such example is a sleeping cat. While not a true black body, it comes close, especially if it's in a sunbeam and refuses to move. The fur absorbs everything: light, sound, expectation. In return, the cat emits only gentle warmth and low-frequency purrs of contempt. Let's take a moment now to consider Wien's displacement law, which says the hotter something gets, the shorter the wavelength it emits. In practical terms, this means that angry teapots glow blue before achieving escape velocity. This is also why the sun emits visible light, while your soup emits only infrared regret. Now, photons. Ah, yes, the adorable children of light. Photons are massless particles that behave as both waves and particles. This makes them extremely indecisive and frequently misunderstood at parties. Sometimes they bounce. Sometimes they wiggle. Sometimes they pass right through glass and don't say goodbye. Photons have no rest mass, and they travel at the speed of light, which, conveniently, is the only speed they know. They are very punctual. They also do not respond to text messages. Sometimes, late at night, photons emitted from distant stars arrive at your pillow after millions of years of travel, only to be absorbed by your forehead and forgotten. What a tragic romance. What an elegant waste of time. Let us now close this section with a reflection on the cosmic microwave background. This is the faint echo of the Big Bang, a whisper of ancient warmth that still hums throughout the universe. It's like a baby monitor left on for 13.8 billion years, broadcasting static from creation's cradle. Comforting, isn't it? In the next section, we'll touch upon heat death, spontaneous refrigeration, and whether your fridge light has developed a personality. But for now, just breathe and imagine a photon gently tucking you in. The heat death of the universe sounds dramatic, and it is, but not in a loud, crashing sort of way. No, it's more like a long, slow sigh from a universe that's finally run out of interesting things to do. Heat death isn't about explosions or flames. It's about balance. Everything reaching the same temperature. A perfect, unchanging sameness. Like a never-ending dental waiting room with no magazines, just soft jazz and the slow decay of potential. Entropy, you see, always increases. It's the one rule the universe refuses to break. Like an overly enthusiastic hall monitor with a clipboard made of stars. One day, far, far in the future, every star will burn out, every spark will settle, and the universe will lounge in a sort of lukewarm eternity, wrapped in cosmic sweatpants, with nothing left to microwave. But until then, we still have refrigerators. Now, a refrigerator is a marvel of thermodynamic rebellion. It takes warm air and rudely removes its energy, compressing and expanding like an indecisive accordion. The result? Cold snacks. But inside every fridge, there's a little secret. Behind the crisper drawer, deep in the hum of the coils, lives a soul, an ancient awareness, forged from half-eaten leftovers and forgotten birthday cake. Some say the fridge light never truly turns off, that it waits, watching, judging your midnight cheese decisions. Is it lonely? Possibly. Is it sentient? Unclear. Does it know when you're out of pickles? Always. Now, let's take a moment to think about spontaneous refrigeration. This is a purely theoretical event where an object becomes colder without any energy input, simply out of sheer stubbornness, much like your uncle at family dinners. No one has ever witnessed this phenomenon directly, but there are whispers of popsicles that refroze out of spite. Speaking of spite, let's not forget the noble thermodynamicists, those brave scientists who try to make sense of this endless chaos, while their coffee slowly cools and entropy mocks them from the corner. They wear lab coats, not for protection, but to feel something structured in a disordered universe. Some of them even name their equations. Others quietly talk to steam. Let's pause here and imagine a cup of tea left on a windowsill in winter, cooling, not just in temperature, but in spirit. The leaves inside swirl sadly, murmuring secrets of forgotten kettles. And above it all, the second law of thermodynamics hovers, softly reminding us that warm things become cool. Order becomes disorder, and everything in the universe slowly, eventually, naps. In our next section, we'll dive into imaginary gases, reversible sandwiches, and the legendary thermodynamic chicken of Constantinople. But for now, let your thoughts dissolve like sugar in lukewarm tea. flavorless, weightless, inevitable. Let us begin with the ideal gas, a concept so perfect, so theoretical, that it only exists in the dreams of undercaffeinated physicists. The ideal gas is polite. It doesn't interact with its neighbors. It follows every rule. It never cuts in line. But imaginary gases, oh no, these are quite different. These are gases that don't expand. They meander. Don't fill a container. They haunt it. And instead of pressure, they exert disappointment. One such example is whimsy gas, a hypothetical substance made entirely of mood swings. Its pressure varies based on ambient sarcasm, and its volume responds to passive-aggressive remarks. A lab once tried to store it in a balloon, but the balloon developed stage fright. Another is fluffonium, an ultralight gas made entirely of size. It is said to collect beneath theater balconies and has been blamed for spontaneous monologues. Now, let's discuss a key concept in thermodynamics: the reversible process. In theory, this is a change that can be undone perfectly, with no loss of energy. In practice, it's a bit like trying to untoast bread or reassemble a broken cookie, using only the power of regret. A classic thought experiment involves a reversible sandwich. Suppose you build a sandwich in a vacuum under controlled conditions while whispering equations into the lettuce. In theory, you could unmake the sandwich, turning mayonnaise back into eggs and lemons, bread into wheat, turkey into a confused bird, which brings us to the legendary thermodynamic chicken of Constantinople. According to dubious scrolls, this bird was once so perfectly insulated that it maintained a constant internal temperature across all of recorded history, neither cooked nor raw. It hovered in a culinary limbo, radiating gentle confusion. The chicken was said to defy entropy, to lay eggs of equilibrium, to peck softly at the boundaries of time. Some say it still roams the universe, clucking in iambic pentameter. A physicist once tried to trap it in a chamber, but the chicken merely stared, and the chamber lost all measurable pressure out of respect. Let us now consider a brief pause and imagine a balloon. filled not with helium, but with forgotten dreams. A thermometer, measuring only your feelings. A gas constant that insists on being called Randall. These are the moments that make thermodynamics worth whispering about. In our next installment, we'll explore the entropy tango, how Kelvin got his name, and what happens when a heat engine decides to become a poet. But for now, let yourself settle like dust in a sunbeam. Slow, aimless, thermodynamically adorable. Imagine a ballroom at absolute zero. Still, silent. Every particle frozen mid-curtsy. But just above zero, chaos begins to hum. Entropy enters, wearing velvet slippers and a monocle made of uncertainty. Entropy does not ask permission. It glides between particles. It twirls probability. It dips order and spins it dizzy. The entropy tango is not about winning. It's about letting go, slowly, of every ounce of predictability you once cherished. When two molecules meet on the dance floor, they exchange more than energy. They trade gossip, secrets, perhaps a shared memory of being water vapor in a younger universe. And then they part, never to collide again, except maybe at a thermodynamic convention in Toledo. And now, a question. Why is absolute zero so unattainable? Because it's shy. It retreats whenever approached, like a reclusive artist or a quantum raccoon. At 0 Kelvin, motion ceases. Entropy hits pause. The universe takes a nap so deep, even dreams have to whisper. Speaking of Kelvin, let us now unbutton the waistcoat of time and discuss Lord Kelvin, the temperature scale's namesake. William Thomson, Lord Kelvin, was a man of many talents. He could calculate the thermal conductivity of pudding with a single glance. He wore bow ties made of steam. His favorite pastime was naming units after himself, a hobby shared by only the boldest scientists. Kelvin, as a temperature unit, does not use degrees. Number, that's far too informal. It just says Kelvin like Cher, or Prince, or soup. Now, let's shift to the poetic dreams of machinery. Heat engines, these noble devices, consume thermal energy and do work. But sometimes, when the lights are low and the gears are sighing, they compose haikus. A simple steam engine once wrote, "I take your warm thoughts, turn them into motion, friend. Still, I feel so cold." A Carnot engine once fell in love with a boiler. Their love was highly efficient, but ultimately reversible. Even refrigerators, those cool custodians of leftovers, have their own verses I hum in the night, preserving forgotten meals. I envy the stove. Some machines go beyond haiku and begin composing heat sonnets. These are typically 14 lines long, but in binary. Now, let's meditate briefly on the lost zeroth law of thermodynamics. It says that if system A is in thermal equilibrium with system B and system B with system C, then A is with C too. It's basically the if your friend is my friend, then we're friends law of temperature, a thermodynamic trust circle. Pause with me now. Imagine a room where every object is the same temperature. The chair, the cup, the spider in the corner, reading a newspaper. No heat flow, no surprises. Just perfect mutual understanding and soft thermal cuddles. In the next portion of our nonsense voyage, we shall unravel Maxwell's Demon's grocery list, debate with a calorimeter, and gently tuck in an exhausted Bunsen burner. But for now, rest your thoughts. Feel your own entropy increasing ever so slightly, and allow the molecules of your mind to dance one last entropy tango before dreams arrive. Now, Maxwell's demon is not a demon in the spooky sense. No horns, no pitchfork, just a tiny, overly confident being, like a squirrel with tenure, who guards a microscopic door between two gas chambers. Now, what is the demon's job? To let fast-moving molecules go one way and slow ones the other. A gatekeeper of kinetic enthusiasm, a sorter of invisible marbles, Scientists once feared the demon might violate the second law of thermodynamics, but upon further inspection, they realized the demon just had very strong opinions and poor bookkeeping skills. It turns out he was too tired to break the laws of physics. He just wanted a snack. Which brings us to the demon's grocery list, discovered etched into a chalkboard by moonlight. 1 jar of entropy spread, 2% chaos milk, low temperature toast, irregular pasta, dark matter for stew, quantum coupons, expired, but still emotionally valid. Now, across the lab, we hear a soft, metallic sigh. It's the calorimeter, awakened from a nap. The calorimeter's main job is to measure heat, but every once in a while, it asks questions. Am I merely the sum of the energies I record? Is heat just misunderstood love? Why does no one ever ask how I'm feeling? The answer, of course, is yes. And also, maybe, but mostly, not at all. In the far corner, we find the Bunsen burner, a brave flame, a steady soul. But even it needs rest. Each night, it dons a tiny silk nightcap, extinguishes its pride, and whispers a bedtime story to itself. Once upon a time, in a land of constant pressure, there lived a noble spark. It dreamed of combustion, but only when the timing was right. A nearby test tube listens in, cradling a single droplet of wishful thinking. And what of the beaker? The beaker dreams of being a wine glass. It's never said aloud, but deep down, in its thick, borosilicate walls, it longs for candlelit dinners and being swirled dramatically by moody poets. The thermocouple, meanwhile, is writing fan fiction about phase changes. In its latest installment, ice falls hopelessly in love with steam, but their love is forbidden because of latent heat. And finally, we reach the periodic table blanket, a large woolen chart that covers the whole lab. Every night, it tucks in the elements. Hydrogen gets extra fluff. Helium floats above the sheets. And argon insists on its own blanket because it's noble. Let us now exhale, gently, like CO2 escaping a lukewarm soda. In the next phase of our strange thermodynamic slumber, we will examine the socio-political structure of molecules in a gas cloud, the lost language of thermometers. and how to gently discipline a rogue entropy spike. But for now, sleep walks quietly into the lab, and everything grows still. We begin now in a cozy, drifting gas cloud, not too dense, not too diffuse, just enough to hold a polite argument. Around here, molecules aren't just particles, they are citizens, floating in governed chaos. They organize into three groups: the fast ones, who consider themselves progressive; the slow ones, who prefer traditional trajectories; and the occasional rogue ion who just wants to dance. They gather in an ancient structure known only as the Chamber of Kinetics, where motions are voted on, collisions are negotiated, and new vibrations are introduced with ceremonial fanfare. Their leader, Chancellor Exiton, a radiant particle with a penchant for dramatic speeches and occasional fluorescence. Each week, the molecular senate convenes. The noble nitrogens debate rotational freedom. The hydrogens propose lighter taxations on translational movement. The noble gases remain aloof, refusing to bond emotionally or chemically. And yet, despite the occasional inelastic collision, the chamber operates with remarkable disorder, which is, ironically, how they define peace. Now, somewhere nearby, suspended like a forgotten bookmark in a mug of lukewarm tea, we find the thermometer. Most believe thermometers simply measure temperature, but in truth, they listen. Each tick of mercury, or digital chirp, is a syllable in a language spoken between the atoms and the void. Thermometers hear the hum of heat, the sigh of cooling tea, the emotional distance between boiling and freezing. The mercury thermometer speaks in elegant cursive, swirling up and down its glass column like a dramatic letter to an ex-lover. The digital thermometer, on the other hand, is blunt. It texts you numbers, often with attitude. 98.6 degrees Fahrenheit. No emotion, just facts. But you can feel the judgment. Infrared thermometers, they whisper in beams of invisible light, gossiping with photons about who's been running a fever. Meanwhile, deep in the junk drawer of a forgotten laboratory, lies the ancient Galilean thermometer, floating glass bubbles, colored like candy, rising and sinking in a lazy, meditative ballet. A temperature scale powered entirely by whimsy. Let us take a breath here. Inhale, like vapor drawn toward a cool surface. Exhale, like heat escaping into the night. Now, if you listen closely, past the whir of ceiling fans and the ticking of radiators, you may hear the secret lullaby of thermal expansion, a gentle stretching, a molecular bedtime yoga. For in the realm of soft-spoken science, nothing truly rests. It just vibrates a little more slowly. In our next segment, we will consult the oracle of heat capacity, visit the phase change spa, and interpret dreams as told by isolated systems under constant volume. But for now, let your thoughts drift like molecules, unaware they are being watched. Softly, thermally, nonsensically. Let us step gently now into the misty chambers of the oracle of heat capacity, nestled between the folds of space, a few degrees above T and just below toast. The oracle sits in stillness inside her chipped ceramic mug, adorned with mysterious stains from experiments long forgotten, each one a symbol, each one slightly coffee-scented. Around her, the air itself holds its breath. To speak with her, a question must not only be asked, it must be felt. Someone once whispered, "What is heat, if not just frantic love between molecules?" And the oracle blinked once, then answered, "Heat is the memory of motion. Temperature is its diary, and heat capacity is how many pages the diary holds." We sit with this, let it settle in our beaker minds. She continues, "Some materials feel everything. Water, for example, is a poet. It takes heat into its soul and holds it close, changing little on the outside. But metals? Metals are drama queens. They blush with every calorie. Touch them, and they shriek with temperature. A breeze rustles the oracle's notes, scraps of thermal wisdom written in invisible ink, visible only during phase transitions. She recounts a parable. There once was a copper spoon and a ceramic bowl. The spoon said, I heat quickly. I am passionate. The bowl replied, I warm slowly. I am deep. They stirred soup together and became equilibrium. The oracle teaches that heat capacity is not a contest, not a race. It is a conversation between a material and the universe. When energy comes knocking, she says, heat capacity decides whether to open the door wide or peek through the blinds and wait it out. She turns to you and asks a question of her own. When you receive warmth, do you react with flair, or do you absorb it quietly and let it become part of who you are? She's not just talking about thermodynamics anymore, but you nod slowly as if you understand. Around her, substances of every kind, graphite, ethanol, quartz, sit cross-legged in meditation, each holding a tiny candle. They are not burning. They are remembering. And as the oracle lowers her voice to a whisper, she leans in and says, the universe is not asking you to burn brighter, only to understand how much warmth you can hold before you must give some away. Then she closes her mug lid once more. The glow fades. The lesson lingers. And now, the conclusion. If you've made it this far, then your temperature has likely dropped a degree. Your entropy has settled into its favorite chair, and your thoughts are curling up like steam against a cold window pane. This was, and always has been, a nonsense lecture, not meant to teach, only to soothe. A journey through scientific shadows, lit dimly by candlelight and softly spoken silliness. If you enjoyed this, please like the video, subscribe to the channel, and ring the gentle, thermally resonant bell icon. AI tools were lovingly used to help shape this creation. See the description for more details. And now, sleep, dear listener. Let the second law keep you warm. Let your entropy increase. Just enough. And remember, somewhere, Maxwell's demon is also falling asleep on the warm side of the chamber. Good night, and may your dreams be endothermic.